My name is Hanan Syazwani binti Maznan. I would like to explain about the theory of amplitude and phase shifting (APSK). Amplitude and phase shifting (APSK) is a digital modulation scheme that conveys data by modulating both the amplitude and the phase of a carrier wave. In other words, it combines both amplitude shifting (ASK) and phase shifting (PSK). This allows for a lower bit error rate for a given modulation order and signal-to-noise ratio at the cost of increased complexity compared to ASK or PSK alone. There are many APSK constellations. Circular constellations are the most common. There may be multiple circular constellations of the same order. For example, 16 APSK could be implemented using a 1-5-10 constellation or a 5-11 constellation. Increasing the number of rings decreases the bit error rate but increases the peak-to-average power ratio. Other APSK constellations include triangular, rectangular, and hexagonal constellations.
Traveling wave tube amplifier is a high-power, high-frequency amplifier that built using traveling wave tubes. The figure shows block diagram of traveling wave tube amplifier. Operation happens when anode plates equals 0. The axial electric field is at a node. Electron beam is unaffected. When it at positive node, electron moves in opposite direction, causing acceleration of electron. When axial field at negative antinode, electron overtake negative field effect. Electron modulated velocity and second waves is induced in helix.
Let us see the coding for APSK modulation and demodulation. Firstly, we will set the values of vectors or constellations for the modulation as m, and set the PSK ring radii as radii. In this case, we set 3 values for each parameter. Note that the sum of m must be positive integer power of 2, meaning that the square root of the sum should be a positive integer and not decimals. Then we will put the sum of m as the input values of x using suitable commands. Then we will use the command apsk mod to apply APSK modulation to the data. To plot the output, we use the command scatterplot. Next, we will try to apply APSK modulation with phase offset. The coding is almost the same as the previous one, but this time we will use 2 values for m and use the command ph off to set the offset value. The sum of m also needs to be positive integer power of 2, and the value of phase offset must be less than the corresponding element of 2 times pi over m. In this case, we set the phase offset value as pi over 6. Then we use the same commands as the previous modulation coding to plot the output. The next APSK modulation condition is modifying symbol ordering, where the plot will be for gray mapping and there will be bit data for each point. The coding until when the input is put in the variable x is the same as the previous APSK modulation. We will use the command de to pi to generate the bit data and set the MSB at the left side. Next, we use the command apsk mod plot constellation and set the input type as bit to plot the output.
With custom mapping. This custom mapping happens to be another gray mapping. Firstly, we create a custom symbol mapping vector here. Then, we apply APSK modulation with a custom symbol mapping. Then, we plot constellation. Binary input is used to highlight that the custom mapping defines different gray symbol mapping.
APSK modulation to input bits. The first line explains the number of circles in each state, where the first state is 8 circles, second state 12 circles, and so on. While the second line shows the radius of each circle in each state from main point. 0.8 refers to the innermost state radius from main point, while for the second state is 1.2 followed by the third and the fourth state. The third line is where the bits per symbol being calculated using the equation, and m can be obtained from the summation of all circle equals to 64 bit. For the fourth line is an equation to obtain the x-axis value. The fifth line explains the apply a PSK modulation using data and name value output. The sixth line explains by passing through a channel with a 25 dB signal noise ratio, and the last line is by plotting the received constellation using a scatter plot.
Next is demodulation, 16-bit. Demodulate a 16 APSK signal that has an unequal number of constellation points on each second. Then plot the received constellation here. Then define vectors for modulation order and PSK ring radii. Generate random 16-array data symbol. Then apply a PSK modulation to the data. Then pass the modulated signal through a noisy channel. Then plot the transmitted reference signal points and the noisy received signal points. So, as we can see in this figure, the constellation warping, which is due to the gain compression of the amplifier operated near saturation, refers to the situation where the points on the inner ring with lower energy are more amplified than the points on the outer ring, which have higher energy. As a result, the constellation collapses towards the outer ring, and this is due to AM/PM characteristic. Moreover, the outer ring is phase shifted with respect to the inner ring because of the AM/PM distortion, and the performance can be severely degraded. In addition, as you can see in this figure, each point is spread in cloud centered around the effective warp constellation. We refer to this effect as clustering, and it is equivalent to have ISI in the received signal.
The next step of demodulation is 32-bit demodulation. As usual, the vectors and radii is first set at certain values, then we use APSK mod to modulate the input. The command COM constellation diagram is then used to generate the points and the reference constellations. Then we use APSK mod to modulate the data. Next, like the previous demodulation, we will let the signal pass through a channel with noise by using the command awgn. Then we used const diagram APSK to plot the constellations. Only then, APSK demod will be used to demodulate the data and compute soft bits.
Demodulation 64-bit. The first line explains the number of x mark in each state, where the first state is 8x, second state is 12x mark, and followed by the next state. Second line explains m can be obtained by adding all the x marks in each state and obtain the 64-bit, and modulation order can be obtained. The third line explains radius for each state distance from the main point, where 0.5 refers to the distance between the innermost state and the main point, and 1 refers to the second state and follows by the next state. Fourth line refers to the x-axis value to plot data. The fifth line creates a custom symbol mapping vector. The sixth line is to modulate data and plot constellation. The seventh line is the demodulation of a received signal, and the last line is used to verify the demodulated signal and equals to original data.